Alright, so today we are going to use this online lecture to have a review of the materials for the second test, which is scheduled to be next Wednesday, April 1st, in the class hours from 4:30 to 5:45. And today we are going to use, let me share my screen first. Share my screen. So we have already uploaded these tips for the midterm 2 to the canvas. You can view this in the exam folder as well. So here, how to succeed in the second test. The topics or the materials covered in the second test will be lecture 9 to 14. So only those lectures. It covers the materials like MOSFET IV characteristic, including the sub-threshold behavior. And also we talk about the CMOS inverter, and we have the operation principle and the voltage transfer curve, noise margin, those concepts, and then the delay estimation, and also the energy and power estimation for the CMOS inverter. So this is the topics we have for the second midterm. And next, let's look at the abilities you are expected to have. So the first one is the ability to draw and analyze a band diagram of a MOSFET, let's say the NMOS, N-type MOSFET, along the channel direction when the gate voltage increases or the drain voltage increases. So what does this mean? So let me show this sketch of the band diagram. So if you look at the MOSFET structure like this, so vertically we have the MOS structure, and this is from the gate to the channel or to the body substrate. And we have looked at this band diagram in lecture 8 already. So if you look at this direction, this vertical direction, the band diagram looks something like this. So where you have MOS, so this metal, you have a single Fermi level, and then oxide has larger band gap, and then you have the silicon and substrate. So here, when you apply the positive gate voltage, you are going to bend down the band of the metal side. So then the silicon band will also be bent, where you have the phi s as a surface potential. So we need to bend down this phi s larger than 2 phi b. Phi b is the distance between the Fermi level to the intrinsic Fermi level. So in order to get this inversion of the channel. And this is what you have seen in the lecture 8 and also in the previous test 1, the first midterm. So we're not going to have this again in the second midterm. So what we care about in the second midterm is along the channel direction, that means from source to the drain. And how does this band diagram look like from the source to the drain? So this means horizontally, we're going to draw this band diagram. Let's say you have the EC, the conduction band edge, or the EV here. So from the source to the drain, we have this kind of two back-to-back PN junction because the source and the drain for the NMOS will be N plus doping. And then for the PMOS, for the NMOS, the substrate will be P-type. So you have two PN junction back-to-back. And then you have this barrier, built-in potential barrier between the source to the gate. And in the equilibrium state, that means we don't have external voltage. Then this Fermi level will be a single level from source to the drain. And now if we increase the gate voltage, like VGS larger than 0, so what will happen here is that, gate voltage positive. So that means we are going to push down the band from the gate. So that means this band edge will be reduced, will be pushed down, and then this barrier between the source and the channel here will be reduced when you apply positive voltage to the gate. And if the VDS keeps at 0, then still from the source to the drain, no current flow. This is equilibrium state. So you still have a single Fermi level, but the barrier here is reduced. Now if you increase the the drain voltage larger than 0, so what will happen here is the positive voltage to the drain, we are going to push down its drain side, the band edge, or push down the Fermi level for the drain side. So then you will have this bend down of the band towards the drain. So now the source Fermi level and the drain Fermi level will be split, because this is no longer equilibrium state. You have the VDS and then you have current flow. So then this is the band diagram when you have VGS larger than 0, VDS larger than 0. And you know the electrons are stored in the source. And then once you push down the gate, and then you reduce the barrier, then the electrons can jump over, and then they can fall down the along this hill, and then it will reach the drain. So this is how the current flow in the MOSFET. So any questions in this slide? If you have questions, you can unmute, or you can type in your question using the chat function here. Now all good? Then let's go back. So the second ability you expect to have is to determine the MOSFET operation region. So we have this cutoff, triode or linear region, or the saturation. So you need to use the voltage bias condition to determine the operation region. So you need to look at the gate voltage, drain voltage, and the threshold voltage. So if you look at the equation sheet we have here, so for the current, we have 3 regions for the MOSFET. Firstly is this cutoff region, where the gate voltage is smaller than the threshold voltage. And to the first order, if we consider the non-channel, then it's almost 0. But if we consider the sub-threshold current, then the current is not exactly 0. It's a small number, but then you still have some current, which exponentially depends on the gate voltage. So in the test, if I ask you to consider the sub-threshold current, then you need to consider this one. But if I don't say that, you can assume to use this first order assumption, where the drain current is almost 0. And then the triode or the linear region, when the gate voltage Vg minus Vt is larger than the drain voltage Vd. So if you have this condition, then the transistor is in the triode or the linear region, where you can have the current equations like this. And then if the gate voltage minus Vt smaller than Vd, then the transistor is in the saturation. And now the drain current only depends on the Vg minus Vt squared. So this is called the square law. And then this is the saturation region. So you need to use this voltage bias condition to determine those 3 regions. And then after you determine the region, then you can calculate the drain current based on the formulas in that equation sheet. And then you should be able to plot and analyze the ID versus VGS or ID versus VDS plots above the threshold and below the threshold. So let's look at the ID VD plot and ID VD plot. So this is ID versus VDS, and we have this kind of curve, and you have different curves here because the VG is increasing from here to here. And here you have this boundary between the triode and the saturation region. So here you can look at the turning point here where it becomes flat. So you have this turning point. So this turning point is important because it's a boundary between this triode and saturation, where you can have this condition Vg minus Vt equals to Vd at this turning point. So the second one is this ID versus VGS. And then this is in the linear scale of the drain current. So you can draw this kind of ID VGS curve. And then this is the threshold voltage. And another turning point here is where the curve becomes linear. After here is linear. So this will be the triode region. So in between here is the saturation region. So this is ID versus VGS. So those two plots are following the first order equation as we show here. But if we consider some second order effects, then we can do some modification of these plots. So one of the second order effect is this so-called channel length modulation effect, which basically says that after you reach the saturation region, still the current will further increase with the drain voltage. It no longer saturates if you consider the channel length modulation effect. This is because this is like the MOSFET, this channel. You have this pinch-off point where you reach the saturation. But further, if you increase the VDS, this pinch point is going to shift to the left. So effectively, the channel length is reduced. And you know the current is proportional to W over L. L is in the denominator. So if L reduces, then the current will increase. So that explains here why the current does not saturate. So again, in the test, if I tell you to consider the channel length modulation effect, then you need to take this into account. Otherwise, you can assume the first order equation. And another second order effect is this subthreshold. So this is below this threshold voltage in the ID-VGS curve. So it's very small, so it's very hard to visualize. So in order to see this small number, you have to take the log scale of the drain current. So if you take the log scale and replot this curve, then you can see this part. So this is below this threshold. So below this part is a straight line in the log scale. That means this is exponential function. So here the slope of this one is defined as the subthreshold slope, and is equal or larger than 60 millivolts per decade. So what does this mean? This means for the current reduced by 1 decade, that means 10 times, you need to reduce the voltage, gate voltage, by 60 millivolts. So this is the definition of this subthreshold slope. Again, if I ask you to consider a subthreshold, then you should consider this, but otherwise you can assume this is close to 0. Any questions here? So got a question, isn't S the inverse? You're right. I mean, to be more accurate, S is the inverse of the slope. Yes. And then let's go back. Okay, so here we just said saturation current no longer saturated if you consider the channel length modulation effects. And number 6, understand the definition of the on-state current I on and off-state current I off. So here the on-state current is defined as the VGS equals to VDS equals to VDD. So basically this is the maximum current you can get out from this transistor because those two voltage reach the maximum, which is the power supply VDD. And then I off is defined as the VGS equals to 0, but the VDS is still VDD. So this is defined as I off. And for the I off, actually, you can get it from this subthreshold plot. So it's this point. If here the VDS equals to VDD, then this point will be the I off. And then this point will be the I on, where you reach the maximum current. So I see some questions from the chat. Does the subthreshold swing influence I off? Does the subthreshold swing influence I off? Yes. So yes, so that depends. If your transistor design, say somehow your threshold voltage is fixed, then if you change the slope, right, then you see you will have different I off points. So then this one will be, for example, S equals to 70 millivolts per decade. So the smaller this number, the steeper the slope, because as you just mentioned, it's 1 over S. The slope actually is 1 over S. Okay. So then let's go back. So number 8. Understand the differences between N-type and P-type MOSFET. So you know everything is reversed, like the doping and the source and drain dopings, and it's changed. For NMOS, it's N plus doping. For PMOS, it's P plus doping. And also the voltage polarities are reversed. So for the PMOS, like all the VGS, VDS, and threshold voltage are all negative numbers. But as we discussed in the class, to make it simpler for you, you can treat all the voltages in the PMOS as the absolute value. So if you use absolute value of the VGS, VDS, and threshold voltage, then for the PMOS, again, you can use the IV equations here for the PMOS if you treat all those numbers as the absolute value of the PMOS. So this is the difference between NMOS and PMOS. And then we talk about the CMOS inverter. If you have NMOS pull down, PMOS pull up, and then you form an inverter. So this is to switch your signal from high to low or low to high. And for the CMOS inverter, the basic function will be this voltage transfer curve, VTC, and understand the definition of noise margin and then the Vm voltage. So we are talking about this kind of VTC curve. So it's a relationship between the input voltage and the output voltage. So as you sweep the input voltage from 0 to VDD, then your output voltage will switch from VDD to 0. And you can define the Vm points by drawing a straight line with like 45-degree angle here. So then this intersection will give you the Vm points, where the Vm equals to Vi equals to Vo, because input equals to output at this node, at this point. So this is for the Vm points, and then for the noise margin, it's defined as when the slope of this VTC curve becomes -1, so then you will get this point. And then from here up to this point, you can think the input signal is 0. So that means if you have some noise within this range, still the output will maintain like high. So that's why this is a noise margin for the input 0. And similarly, you can have the noise margin for the input 1 here if you take the slope -1 here. So this is the VTC curve. And then match the condition for the CMOS inverter. And draw the VTC curve under unmatched condition. So here for the matched condition, then you will have the Vm equals to half VDD. And for the matched condition, the CMOS inverter, basically the NMOS and PMOS will be equivalent. So NMOS is for pull down the output, PMOS is to pull up the output. So if it's matched, then they will have the same switching speed. So that means the TPLH will equals to the TPHL if you have this matched condition. So everything is symmetric between the NMOS and PMOS. So to make this matched condition, you need to satisfy some criteria here. So first is this threshold voltage for the NMOS equals to the threshold voltage for the PMOS, of course, absolute value. And then second one is this coefficient in front of that voltage term in the current equation. Is this mu n COX W over Ln should be equal to mu P COX W over Lp. Basically, the strengths of the NMOS and PMOS are the same. And typically for the same technology process, then the COX and the L are the same for the NMOS and PMOS. So essentially, you only need to keep the mu n Wn equals to mu P Wp, or in other words, Wp over Wn equals to mu n over mu p. So the transistor width ratio inversely proportional to the mobility ratio. And you know, for the NMOS, electrons move faster than the holes in the PMOS, and then the mu n is larger than mu p. So actually, PMOS Wp will be larger than Wn if you want to reach this matched condition. So then for the unmatched case, then you know this VTC curve will shift to the left or shift to the right, depending on the relative strength of the NMOS and PMOS. So if NMOS is stronger, then the VTC curve will shift to the left. Why is that? Because NMOS is for pull down. So if NMOS is stronger, for example, this part is larger than this part, then the NMOS will pull down the output earlier. So then this VTC curve will shift to the left. So any questions here? So I see one question. How can we calculate noise margin under unmatched case? Okay, so we don't require the, this is sent to me privately, Nestle. So later maybe you can send this message to everyone, so everyone can read this. But I can repeat your question here. So you ask, how can we calculate noise margin under matched case? So this is not required in this course, and the equations we have in this equation sheet is for the matched case, I think, and we don't require how to calculate the noise margin under the unmatched case. But conceptually, you need to understand if, let's say, like this, if NMOS is stronger, then you shift to the left. The noise margin for the input 0 will become smaller than the noise margin for the 1, conceptually. So we only require this one. We don't require how to calculate this under this unmatched case. Okay, so this is this question. And then ability to calculate delay in a CMOS inverter using two methods, average current or the RC equivalence. So here the NMOS is for pull down, PMOS is for pull up speed. So I do see some questions here. Will we could trial the saturation currents and differentiate to calculate? Yes, you are right. So if you want to really calculate the noise margins, then you need to do that. Because NMOS and PMOS, one is in saturation, one is in the triode. If they have different, even they are unmatched, you can still use the current equation for the NMOS and PMOS, but one is in the triode, one is in the saturation, and then you can do the differentiate like we did in the class. But we didn't require this. So let me see. The delay. Okay. So the first method is to use this average current, and we have two kinds of delay. One is the TP-HL, high to low transition for the output. So that means NMOS is working because NMOS is for pull down, pull the output from high to low. So then here the average current assumes that the output change from 100% to 50%. So you have the CVDD divided by 2. And then this is essentially the charge you take out from the output capacitor. Then divided by the current, give you the time. So the average current is the initial point plus the final point divided by 2. So what is the initial point? Initially, before you start discharging, then the output is at VDD. Of course, input now is kept at VDD. And so then the final point is input VGS is still VDD, but output is already changed from VDD to half VDD. So the only difference is that output becomes half VDD. And you can check that typically initially the transistor is in the saturation and then the final point is in the triode. So you can plug in the saturation current and the triode current and then take the average. So you will get this average. Then you can plug in here and then get the TP-HL. Similarly, you can get the TP-LH. So it's just replace the NMOS parameters with the PMOS parameters because PMOS is for the pull up. So this is the first method. And then the second method is this RC equivalence. So if you just approximate the transistor as resistor, then you just consider the time constant because it's a first order RC circuit. And the time constant tau is RC. And then for the TP-HL, we have this 0.69 RC. This 0.69, this coefficient, is because we change the voltage, the output by 50%. 50% give you the natural log 2, which is 0.69. So this is the RC equivalence. And in the test, I will let you know which method to use. If we use the average current, then you have to use that. Okay, so this is number 13 now. Okay, so calculate dynamic energy in one clock cycle and dynamic power given the clock frequency. Understand dynamic power is due to the charging and discharging or the short circuit current, basically the Joule heating. So the energy in one clock cycle is just a CVDD square. And in those two rising edge, there's one rising edge and one falling edge. So each of those transition, high to low, consume half CVDD square, and low to high consume another half. So in total is CVDD square. And then the dynamic power will be just this energy multiplied by the frequency, clock frequency. And then sometimes we have alpha here representing the activity factor. So this is a switching activity because not every cycle you are going to switch. So the percentage or the probability of the switching is given by this alpha. So for the standby leakage power, it's just due to the off-state current. So this is a subthreshold current, and this I off multiplied by VDD will give you the standby leakage power. Okay, so here got one question. Is it true that as long as VTP equals to VTN, no, not exactly. The answer is no. VTP equals to VTN just guarantees that the point where you start decaying this output or here are the same, but how fast it reaches to this point depends on the current. So still you need to satisfy the matched condition, those two conditions together to make it totally match. So you should have this VTN equals to VTP and also this one, the second term here. You need to satisfy both to get the matched condition where you can get the same noise margin for the 0 and 1. So you have to satisfy both. Okay, so this is all right. So those are all the bodies you need to take care of, and then some tips. Practice the practice exam. So we uploaded one of the tests for the second midterm from one of the previous semesters to the Canvas under the exam folder, and you can take a look. So the materials in that one may not be exactly the same as we have in our test because the schedule of different semesters may be different. So in that practice exam, it may have some scaling questions. So we don't have that. And then redo the homework and review the lecture examples. We will go through the solutions for homework 3 and later today. And then bring a real calculator, and this cheat sheet doesn't matter now because online I don't really enforce this. You can have open book, open notes, that's fine. So, but if you still is in classroom, then we will have this. But we provide the equations and the constant parameters at the end of the exam papers. Again, pay attention to the true and false questions because there will be penalty if the answer is incorrect. So the best strategy is leaving it blank if you are uncertain about it. So this is the same as the first test. So be careful about this true or false. And to get partial credit, write down the appropriate equations first, and then do the numerical calculations step by step. So this is important to get the partial credit. All right, so this is the tips. So any questions? So I will stop sharing.